Hi everybody, this is the problem of the day that we're going to be working on in physics. So we're kind of going a little bit low tech using a whiteboard right here. And what the question we're going to be doing today is to look at a rock that's being fired straight upwards. So we have a 0.5 kilogram rock that is fired straight up at a velocity of 3.0 meters per second. So using the law of conservation of energy, we're supposed to find the maximum height that the rock will reach. All right, so this is a common type of problem that gets a lot of people. All right, but it's really very simple once you see it. And so what we have to think about, first of all, what is a key word that we can use to help us out? And I'm going to demonstrate something with a whiteboard to kind of help you out. All right, so a key word to help you solve this problem: conservation of energy. That's an important thing. So the law of conservation of energy states that energy is not created or destroyed, it just changes form. So what are we going to do here? Well, let's think about that. Energy. The rock is moving initially. So what that tells us is that we've got kinetic energy. Kinetic energy, and I'll call it KE. And the equation for kinetic energy is 1/2 mv squared. All right, so that's our first equation that we're going to need. Now, let's think about this rock for a moment. So this rock is being fired straight upwards. All right, so initially all of its energy is kinetic energy. Kinetic energy is going to be equal to 1/2 mv squared. So that's initial, when it starts off. So let's think about its final kinetic energy, right? Because the rock is moving straight up. At some point, the rock is going to stop because gravity's pulling on it the entire time. All right, so whenever it stops, its velocity is 0. Hence, its final kinetic energy, right, at this point right there is going to be equal to 0. All right, so our final kinetic energy is 0. Now, when we're talking about energies, right, you've heard about kinetic energy, that energy that's due to the motion of an object, and you've also heard about potential energy, which is due to energy that's being stored. All right, so initially, since all of the energy is tied up in motion, our potential energy is going to be equal to 0. Now at the top, that means all of that kinetic energy, whenever the rock stops moving, all of the potential energy that's where all the energy is. All the kinetic energy has been completely converted to potential energy, right? It's stored now because the rock is motionless and it's above the earth. So gravity's pulling on it. So in that case, our potential energy is given by mass times gravity times the height. All right, so now we've got two equations that we can use. We can figure this out because we know something. We can calculate the initial kinetic energy, right? Because we've got a mass and we have a velocity. So we can figure out that initial kinetic energy. Well, that initial kinetic energy, and we'll call this KE sub I, right? I for initial, is going to be equal to the final, we'll call this PE sub F, potential energy. So now I've got 1/2 mv squared is going to be equal to mgh. So now I've got all of these wonderful variables here. We can figure this out. We can figure this out because g is gravity. 9.8 meters per second squared. The acceleration due to gravity. So we know velocity, we know mass, we know the acceleration due to gravity. So all we've got to do is determine height. So let's go ahead and look at height, right? That's our unknown that we're looking for. So let's isolate that variable. Well, we do this by, let's start with mass. Well, to get mass on a side by itself, we're going to have to divide both sides by m for mass. Hey, guess what? Mass cancels out. We don't have to worry about it, do we? All right. 1/2 v squared g times h. All right, so now in order to get h on a side by itself, we're going to need to divide both sides by g, or gravity. Of course, g cancels here. And our final relationship that we need, or final equation, is 1/2 v squared divided by gravity. So I won't complete the calculations. I'll let you do that. But this is important to see that this is the setup. That is the setup that's going to help you figure out this problem. All right, so this has been the problem of the day. Good luck as you work on physics.